All right, so I think I'm the last talk of the day, and for a crowd that likes to think about algorithms and resource allocation and capacities, we're doing a really poor job. So the organizers have asked me to go a little quickly, so I'll not dwell on a few points. This is pretty early stage work. It was Chris Yu, who was an undergrad at Cornell. It was his undergraduate honors work. He's now at CMU. And I'm very interested in getting feedback from this crowd on sort of where the work should go. Many people ask what Kulfi means. The Kulfi is a Indian dessert, kind of sort of ice cream that is not churned, and that's the pun that we're playing off. I would have loved to talk about some PL work, but Vyas told me that there's no PL work at this workshop, so I won't tell you about that. But if you want to ask me about probabilistic or stateful programming languages, I'd love to chat. So this work started out with a bus ride a few summers ago. A bunch of us actually in the room were out at Facebook visiting their networking team, and the head of that team asked, why aren't there more algorithms researchers working on SDN? It seems like we finally have a platform for deploying advanced applications, and we should be able to get away from all the kind of conventional protocols and such that we use. And so we've been basically sort of taking that inspiration and trying to look at the problem of WAN traffic engineering. This is a problem that we've heard a lot about today already. The motivations are, of course, that WAN infrastructure is expensive. Operators have to sort of provide good service, including customer traffic that has tight latency bounds, and also just massive amounts of volume, things like backups and so on. And there's lots of competing objectives that you want. So you want to do things like balance the load. You want to achieve low latency, at least for the customer traffic. You need to be able to work even in the presence of failures or mispredictions. And you want all this to be not too complicated to implement. Just to show you a few of these challenges sort of pictorially, here's a kind of abstract topology. And some of the things that make traffic engineering difficult, even, say, in SDN, is that, well, first, the devices are fairly limited. So they have routing tables that are not enormous, and they can't always be updated very fast. The topologies have some quirks. So even very structured topologies often have sort of sporadic shortcuts or sparse bisections. And then operationally, you can get things like devices and links crashing, or if you're trying to estimate how much traffic you have, you might screw it up, or you might get a traffic burst. And so the challenge is, how can we route traffic while achieving all these nice properties like load balancing and low congestion in the presence of all these challenges. So if you sort of abstract away, I think there's sort of two things that make up a routing scheme. One is, what forwarding paths are you using to carry traffic, say, from some sources to some destinations? And if you have multiple paths, how are you going to map incoming flows that arrive at some source onto those paths? So one thing you might think, and this is really a straw man, is we know the sort of algorithmic presentation of this problem. We can solve it using by solving the multi-commodity flow problem. So maybe we could just sort of directly implement that. So how would this work? We would need to somehow estimate the demands in each time period from historical data. We'd encode the routing problem as a LP, stating some objective we want to optimize for, and then we'd extract the paths from the solution and map that down into routing tables, and then repeat this in a tight loop. And this has a number of limitations, which have been well studied. I guess the main ones are that actually estimating traffic can be difficult. MCF-based approaches can basically overfit. So you can end up, when you have failures or bursts, where they actually perform worse than simpler schemes. And there's just fundamental limitations derived from hardware about how fast you can run this loop. But to get close to optimal, you actually have to run it pretty fast. So there's some seminal work that appeared a couple years ago. There's also early work by Jen and at AT&T. But the idea that sort of broke through was that if you have some kind of centralization, then you can greatly improve performance. So systems like Swan and B4 work by essentially pre-computing a set of paths or computing in sort of big epochs. And they tend to use fairly simple schemes like just k-shortest paths, and then use a solver or a heuristic to compute optimal or near optimal sending rates in response to demands. And these systems have achieved enormous performance improvements in practice. OK, so what we've been looking at in this project is how we could use some ideas from the theory community to improve the path selection component of centralized TE solutions. And so the motivation is that to basically use path selection schemes and randomization to spread out the load and minimize objectives like congestion. So let me give a really brief tutorial on sort of randomized routing. I think for the algorithms folks, this is completely old hat. For many of the networking folks, it may not be. So the simplest form of randomized routing I know is ECMP. So the way ECMP works is you have a set of least cost paths that are computed by some routing protocol, and then traffic gets mapped over those paths by basically uniformly hashing some set of header fields and then picking a path for the entire flow. So this works really well and it's widely deployed. The places where it breaks down are if your topology has some of these shortcut links that I showed before, then you can end up with bottlenecks. So you can have lots of short paths that go over the same bottleneck links, and so you're going to be limited. So there's a way to get around this that Valiant and Brebner and others developed in the early 80s, which is basically to not restrict yourself to shortest paths, but to use basically random paths. So in so-called Valiant load balancing, the idea is that the paths are chosen by selecting some random intermediate node, routing from the source to the intermediate node and then on to the destination. And so this solves the sort of key bottleneck in ECMP because you're no longer limited to just shortest paths. You're taking longer paths, and now you have a large number of diverse paths to send traffic over. The problem, of course, is that if you just pick random intermediaries in a general topology, you can end up with these very long paths, like maybe you go across the ocean to get between 2 points in the United States. So there was this seminal work by Räcke and others, including people in this room, about 15 years ago, where they realized that you could generalize the idea of Valiant load balancing by constructing these paths in slightly smarter ways. So the basic idea is to build so-called routing trees, which are just tree-structured overlays over the topology, where the tree has the property that following a path in the tree maps down to a physical path that is not too much longer than the shortest path that you would have taken otherwise. And so there are some clever algorithms for how you can construct probability distributions over these routing trees. I'm going to call these randomized routing trees. And you can show that these schemes are actually oblivious to demands. So no matter what demands show up in the network, if you route by sampling the distribution to choose a routing tree and then following the unique path in that tree, which happens to have this nice low stretch property, then you will do pretty good with respect to properties like congestion. There's an extension that my collaborator Bobby and some other people looked at a little bit later called Semi-Oblivious Routing. And the idea here is that we can possibly improve the performance of these oblivious schemes by combining a sort of base oblivious set of paths with some dynamic adaptation to the rates that traffic gets sent in the path. And what this means sort of concretely is that if you view an oblivious scheme as a distribution on routing trees, we're going to dynamically adjust that distribution. So we'll weight some trees more or less depending on the actual demands that we see. The paper that Bobby worked on showed that actually this doesn't appear to actually perform a whole lot better than Räcke schemes in the worst case, but it was sort of open if in unrealistic topologies and realistic workloads, if there would still be some improvement. So what we've been doing is basically to implement oblivious, semi-oblivious, and lots of other routing schemes on top of an SDN testbed. And we built a system called Kulfi that has over a dozen different traffic engineering schemes. And we've built simulators and building on top of our phonetic system an implementation so we can actually run experiments and look at the performance trade-offs in these different schemes. So just a few I want to draw your attention to. We have a kind of funny naming scheme that I actually don't like, but just to sort of decode it for you. So this thing I have highlighted here, semi-MCF, MCF, that stands for a semi-oblivious scheme where we're using an LP solver to both pick the paths and pick the rates that traffic goes onto those paths. This next one, semi-MCF k-shortest paths, is basically using the LP solver to pick the rates, but restricting ourselves to just k-shortest paths. This is so-called semi-oblivious routing, so we're using MCF to compute the sending rates over a set of paths that are given by Räcke's algorithm. And then this bottom one, semi-MCF, MCF, FT-ENV, is actually a system that Jen worked on with Martin Chuchara and others a few years ago. And the idea is to use an LP solver to pick a diverse set of paths given a model of demands and failures, and then to use an LP solver again to pick the rates over those paths. So just to show you sort of what these things look like in practice, this is the Abilene topology. And we've drawn here sort of visualizations of different routing schemes. So you see the paths drawn with different colors, and it's a little hard to see probably from this slide, but the width of the path kind of tells you the relative weight of that path in the distribution. So just to show you a couple things, this is showing for just a single source, node 4 going to a single destination, node 2. You see that shortest paths just take one of the shortest paths going there, whereas using MCF to pick the paths takes a very circuitous path, and Semi-Oblivious using Räcke uses these low stretch paths, which gives us lots of diverse paths, but they're not sort of much longer than the shortest paths. Since I'm going quickly, I'll skip through this quickly. So we've built an SDN-based implementation that we use to do hardware experiments. We've built a little test bed that we can use to simulate lots of topologies. And let me start first with a test that we did using the Abilene topology. So the idea was we used our hardware test bed to emulate Abilene, and then we used some synthetic traffic generators based on the gravity model to generate a wide range of demand matrices, and then compared a bunch of these different schemes with respect to congestion. And we actually, to sort of model traffic bursts, we also injected some artificial traffic, basically scaling up the demands between a couple of nodes in the middle going to a single node to look at a sort of pessimistic scenario where there's an unexpected burst. And so the first results I want to show you are some plots of link congestion. So you see actually two different data points here. The top data points are the max congestion. So this is a time series, and in each time interval, what you see is what was the congestion of the most congested link relative to its capacity. And so you see that schemes based on using shortest paths like SPF and ECMP have very high congestion, whereas using an LP solver, that's MCF, is much lower, right around 50%. And using Räcke scheme alone, so this is Oblivious, is somewhere in the middle, and if we combine this centralized TE with dynamic rate adaptation, actually the Semi-Oblivious tracks the optimal scheme, the sort of optimal Strawman scheme almost perfectly. And you see similar results for the median congestion as well. Let me go backwards now, and we also did some simulations on Facebook's backbone data. So here, it's a very similar kind of experiment, except we were running this in a simulator instead of on a test bed, and we did it over a week of data on their inter-data center backbone. So here you see a bunch of different plots. The green is their production system, and so because all the demands that we saw were feasible on that never exceeds 1 max congestion. Blue is Oblivious routing, and then red is just as a kind of baseline what would happen if you just used shortest paths. And you see again both max and median congestion. So one of the takeaways here is that although Räcke's work predicted a polylogarithmic bound, it actually appears to be more like a constant for real-world topologies and workloads. And then more recently, we've been doing a bunch of work looking at lots of different topologies and scenarios. So this is a plot of a bunch of experiments we did using all of the topologies in the Topology Zoo, where we injected faults. So in each time window, in each topology, we took the demands, we routed them using various schemes, and then we failed one of the links, and we allowed the scheme to recover from the failure by basically not changing the paths, but by recalculating the distribution over those paths. And it's a log scale, so it spreads things out a bit more than you otherwise might have. But the thing to notice is that because they're achieving fairly high path diversity, both Räcke's algorithm and the Semi-Oblivious version achieve very low packet loss, whereas a lot of the other centralized T schemes that are sort of here achieve a bit more, and then somewhat ironically, schemes based on using MCF to pick the paths actually do quite badly because they sort of overfit just trying to minimize max congestion. So when failures occur, they can do quite poorly. The other thing to say about this is, I should have mentioned this earlier, that we do limit all of these schemes to a fixed budget. So we don't allow any of the schemes to use an unbounded set of paths. we limited them to, I think in this case it was 3 paths between each source and destination. Okay, one other plot I wanted to show you was sort of the effects on latency. So this is again in our simulator, again using topologies from the Topology Zoo and simulated demands. So one of the things you might think would be bad about using algorithms like Räcke's to pick paths is that they tend to, although they try to get low stretch paths, they do pick longer paths than shortest paths. And so you should see basically the latency increases for traffic that's forwarded using oblivious schemes. And so here we ran simulations for a bunch of these synthetic demands. And what you see is that actually sort of up to about 70 or 80% of the total demand delivered, the oblivious schemes, which are here in green, actually closely track a lot of the other schemes. And then because they actually achieve higher diversity in the presence of failures, so this is run with the same failure scenarios as before, they actually are able to deliver more of the traffic, getting very close to 100% of the demand. They do experience some loss right when the failure occurs. Okay, so I have lots more data, but in the interest of time, I'll skip over it and maybe just conclude by saying I think sort of SDN presents an exciting opportunity for looking at some of these algorithms that have been proposed, well studied. You know, their complexity has been characterized. Some of them have actually been tried out in limited situations, but I think we could actually do them more broadly. And in particular, the sort of better paths that you get from oblivious routing seems like a promising way to solve some of these challenging challenges in wide area traffic engineering while retaining some operational simplicity. With ongoing work, we're looking at working with a large ISP and a content provider to further and refine and evaluate Kulfi and trying to characterize more precisely the set of scenarios under which it appears to do much better than the theory predicts and other cases which are more worst case. If you're interested in trying out our code, we have, as I said, working implementations of a whole bunch of different TE schemes that all run on top of OpenFlow through Frenetic. I'd love to have people try it out. And if anyone is interested in this topic and would like to discuss more, we're, as I said, at sort of early stage, and we'd love to get feedback. Okay, thanks. Ratul?
Just kind of curious, maybe this is a question about Facebook's exact environment, then, because it does have bearing on at least the simulation results. So so one of the things that why we didn't go down this path was because we had rate limiters on the edge. So that suddenly kind of, it's almost like we had infinite demand and we had rate limiters at the edge. So we basically it's not so much the variability in the demand matrix or anything we were worried about. We just want to be fair to everybody else. I wonder if Facebook's kind of similar, like lots of data to send and essentially edge rate limiters. And what that does is that then you don't need, in that world at least, you don't need oblivious routing because your optimization goal there is just maximize throughput, not to deal with uncertainty in demand there. And I don't know if Facebook's kind of similar or not. I would imagine that most of their data, at least between data centers, would be kind of similar, replicating their photos and videos and whatnot.
So yeah, I completely agree. I think the case where this might be most useful is in the context of an ISP where you have customers and you're not shaping them.
Well, except that maximizing throughput, taking advantage of randomization may maximize throughput for any traffic metrics. They're not totally divorced.
Just to follow, it's possible that Facebook, where they peer with an external ISP, what they're doing might be quite useful. Right? Because it's only purely inter-data center traffic which can be rate limited, but there's also traffic that's coming in from the users across ISPs.
So actually, I think, I foresee the Russian now. You skip all the details. Actually, I'm curious about the SDN implementation, right? I mean, like Apple did this oblivious routing stuff a while back, and they probably tried to implement it using like OSPF or whatever MPLS foo that they had at that time. Now the question is like how easy or difficult was it to realize it in an SDN implementation? If you can say anything about like, here's how it made it easy to implement, oblivious routing or semi-oblivious routing.
I don't think I
So
have-
what in SDN did we exploit? Is there anything about SDN that we exploited that was missing from the Applegate paper?
So
I'm looking for like some insight now.
yeah, I mean, there are some sort of modest improvements we made. So like a simple thing is if you, maybe we misunderstood it, although Bobby Kleinberg is a co-author on this and I don't think he misunderstood things. If you sort of not directly implement the algorithms, you can end up with loops. And those loops, so basically when you map a tree edge down to a path in the physical topology and you concatenate these together, you can start creating loops. And eliminating those is always a win, doesn't harm the bounds. So there's things like that you know, sort of the first time we sort of went from paper to code, we were like, well, that's kind of silly. We didn't.
Is that SDN? No, it's not really SDN specific.
No.
More like implementing. Somebody actually tried to implement this theory thing and code something.
No, I mean, maybe the short answer is not really. I mean, basically what you need is a set of paths. And there's interesting questions about how you would, you know, like compact routing kinds of questions about how you might pack all those paths together. And, you know, the more paths, the bigger budget you give yourself, the better you should do. You'll be able to implement more paths. But I wouldn't say we've done anything super innovative there. We've done some sort of obvious heuristics to try to compress these tables, but nothing deep.
You mentioned several times that the Räcke scheme tries not to choose long paths. But as far as I know, that's only kind of indirectly because it's a hierarchical decomposition and because in general minimizing congestion should lead to mostly short paths. But as far as I know, there are no guarantees at all about the path length for Räcke. I mean, in practice, you didn't show in your graphs or tables what the path lengths looked like, which would have been interesting, the average path length.
I think so. This, well, where am I? This is basically showing that, although it's then run through a simulation. So a scheme that uses longer paths will increase the latency. I do have those graphs I can show you later.
No, this is good enough.
Yeah.
Thanks.
So if multi-commodity flow tends to overfit, I was wondering if you tried some kind of regularization using a soft max instead of max, or adding a squares of congestions and loads on links over the network to smooth out the traffic a little bit.
I see. No, we didn't try that. I mean, the work that we did compare against that tried to address this was Jen's work, where she basically ran a series of considered a series of different failures and took sort of the envelope of the demands to try to avoid overfitting for any particular scenario. But that would be interesting to do.
Can you go to the Facebook case now? Yes, I was curious as to why oblivious congestion is like so much worse in the median case.
I don't know the reason for that actually.
So I was just wondering, what is the conclusion that you drew from these evaluations? Like, was there any?
So this was done very early. Chris went to Facebook about a year and a half ago and ran the simulation, and we've not.
Actually, don't you expect that to happen? I mean, in some sense, what it is doing is like it's smoothing out the load, right? So everybody's like, everybody's at like 30%. I think it's like just smoothing out the load. That's why it's the median or something higher, maybe.
The other graphs,
That.
the other graphs have the same behavior. You want to compare several of them.
Yeah.
But also the scales are very different, right?
The median for shuttles paths is. Any question?
Yeah, this is state validation, empirical validation of the effectiveness of semi-oblivious routing. I was just wondering if an interesting theoretical question would be, given a network topology and assuming that you're using this kind of routing, is it possible to determine a traffic matrix that can result in latencies crossing a certain bound or utilization crossing a certain bound? Can you characterize what kind of traffic matrices, given a topology and this routing, can result in some network objectives getting violated?
So I think that would have to be a probabilistic kind of thing, right? Because all of these are based on. But yeah, I haven't thought about that. That seems quite interesting.
My guess is that duality should at least give you for a particular topology, a traffic matrix that might give you bad bound. Characterizing it might might be a little more difficult.
Even a particular example may be useful to understand what is it about a network is.
So my guess would be duality might tell us something.
Okay, yeah, I think I achieved my objective to finish quickly.